In this lesson, we're going to connect the idea of hypothesis tests, which are used to determine if something is fair, and confidence intervals, something that tells us what to expect. And we're going to do this for one proportion right now. Throughout the term, we'll look at comparing averages, we'll look at two proportions, we'll look at multiple averages, but for right now, we're starting with this model. I'm just going to label everything in this base model to understand where it's coming from. First off, p hat, this is telling me that I'm dealing today with percentages. So these are going to be testing claims and creating guesses for intervals involving percents. And this is the name of the model. This tells me that I'm dealing with the normal distribution. When I use the normal distribution, I'm using z-scores. This first value p represents the center of my model, or the average. And this last part, the square root of pq over n, this is my standard deviation. It tells me how my estimates or center will vary. So when I'm looking at these two things side to side here, I just want to note that they both use the same model, and I'm going to keep coming back to this thing. However, if you're just trying to understand broad strokes what the difference is between a hypothesis test and a confidence interval, hypothesis test will answer the question, is it fair? More specifically, should I reject the null hypothesis? It doesn't tell me what fair actually looks like. So if I get a 20% success rate, is that significantly higher than, say, 50%? What about the deviation thereof? So it just tells me if something is fair or not fair. So you can think of a hypothesis test as just answering a yes or no question. If you want to know how is it unfair or how is it fair, then you're really asking a question for a confidence interval. Hypothesis tests just tell us yes or no, reject or fail to reject. Confidence intervals just tells us what to expect. So in a lot of ways, if I know what to expect, I can actually answer this yes or no question over here. So I would say of these two topics, confidence intervals are considerably more important than hypothesis tests, although they're both the same model. They go in different directions, so think of them as being kind of two sides of the same coin here. Confidence interval, I suppose I know a small sample, and let's suppose my sample success rate is p hat. I use that to guess what should happen for the larger population. So when I'm working with this thing, it starts at sample, and it tells me what to expect for a population. Hypothesis tests really work in the reverse there. They start with a claimed value for the population, a p naught, and they analyze a smaller sample, and they look at the likelihood of that sample data or more extreme compared to this claim value for p naught. These go from population, claims at least, to samples. Hypothesis tests will always have the same general setup. For what we're doing, the confidence intervals will roughly have the same setup as well. In particular, confidence intervals are going to look something like the following. You're going to have the center plus or minus whatever distribution you're working with, critical values for that distribution, and a standard deviation-like thing, which we call the standard error. Just as a note, when you're looking at these formulas, I'm starting at sample. So this will all be based off my sample data. So when I look back up here at my model, my center, my standard deviation, I'm going to ask myself, how can I write this, but based off of the sample? So for example, my center was p. That's my population success rate. If I want to say the sample version of p, that becomes p hat. If I'm working within normal distribution, I use z-scores, so I'm going to have z stars for my critical value. My standard deviation was the square root of pq over n. To make it a sample, I'm looking at my sample success rates, p hat and q hat. Labeling this with a little bit of vocab, reminder, this piece here is called the best point estimate. So if I'm trying to estimate a success rate and you say, well, only give me one number to guess it, I could be like, well, I think it's 20% a success rate. If you allow me to say give or take, the amount I give or take is called the margin of error. I will affectionately abbreviate that as the mo. So I want to look at the same kind of combination of symbols here, but now I'm going to do it for a hypothesis test. Reminder, there are 4 steps to a hypothesis test. My first step, I state my hypotheses. Second step, I determine my model. Third step, I'm going to calculate the p-value. The likelihood of the sample data are more extreme compared to the null hypothesis. And for a fourth step, I'll do my conclusion. So reminder for hypotheses, these are always going to look something like null hypothesis p equals some number. I'm working with percentages today, so I'm writing down p. If I was working with averages, this would say mu. If I was working with standard deviations, this would say sigma. For my alternative hypothesis, it's either going to be less, that will be a left-tailed test, greater, that's a right-tailed test, or not equal, that's a two-tailed test. When I determine my model, whatever my problem's based off of, I'm going to use the model that matches up with those symbols. I'm working with the problem for percentages. I would use a model for percentages. Reminder, I have 3 assumptions for both of these: random, independence, 10% rule, and finally large N, at least 10 successes and 10 failures. As a third step, I calculate the p-value. Reminder, p-value is the size of the tail, and part of that process involves finding your test statistic or your z-score. So I'm going to call this my test statistic here, my test stat. And the way I find this is by taking my value. My value in this case will be whatever my sample success rate is, minus the center. The center of my model in this case is a symbol p, divided by the standard deviation. Standard deviation is the square root of pq over n. Now, I just want you to look at these two things side by side so you can see that I really kind of have the same symbols in both of these things that have been remixed to either an interval if I want to guess a range of values, or a z-score when I'm trying to find a single p-value to answer a yes or no question. I'm only going to have one answer here, or I'm going to have a range of answers here. And finally, I have my conclusion. Reminder on the conclusion, if the p-value is low, so if you have a p-value smaller than your alpha, you reject the null. So if the p-value is low, the null must go. Our model for one proportion, p hat is normally distributed with the sample center of p, and a standard deviation of square root pq over n. I've said this a few times. I'm really hoping to kind of drive this home. A confidence interval gives a range of potential values for a parameter based off of statistics. It starts with the sample. The conclusion is about a population. Hypothesis test. This is a process that uses statistics to test a claim about a parameter. So error is unavoidable in both these situations. My other big goal is to make sure that whatever process I do here, if something is telling me that it's fair, it also tells me that it's fair when I'm doing the confidence interval. So I'm hoping my numbers for these two processes match up. Let's take a look and see what's going on. So suppose that I did a warm-up problem here where I was looking at a local high school success rate compared to a national rate for something like percentage of students to pass an AP stats exam. So null hypothesis, their local rate is the national rate of 40%. They think they're better. They have an alternative hypothesis where they're testing if they're greater than the 40%. If you go through this hypothesis test with 80 successes out of 120 trials, you would end up with a p-value of 0 plus. So what this p-value is telling me in this case, since this is astronomically small, my p-value is low, so I would reject the null. If I'm rejecting the null, this must mean I have evidence of the alternative. So in other words, I have reason to believe that their success rate is more than 40%. In some ways, this is a really satisfying answer. So I have evidence that they're better than the national percentage. In other ways, it's not so satisfying because I don't actually know how good these students did. Did they get a 41% success rate? That's better than 40. Or are they all the way up at like 90%? So there are a lot of ways that I can be better than 40. This alone only tells me that they are better. If I want to know how good they did, this becomes a question for a confidence interval. So I'm going to create a 95% confidence interval. And I'm just going to skip straight to the answer. I got a low value of 59.6 using 80 and 120 and a critical value of 1.96. And I got a high value of 73.7. I strongly recommend going through this process to verify these numbers. If you'll notice, my interval is larger than 40%. Both the low number and the high number of my interval is bigger than 40. Why is this a big deal? Well, this tells me I have reason to believe that the actual success rate is more than 40%. That's the same thing as my conclusion over here for this hypothesis test. What's the big win for this instead? Instead of just saying that I think it's more than 40%, I have reason to believe I'm 95% confident that it's between 59.6% and 73.7%. So if anyone asks me a follow-up question like, do you think they're 80% successful? I could say, well, I don't think that, but maybe it's somewhere between this and this. So just to really drive home what the p-value is, though, because this is important to making this conclusion over here, the p-value is the likelihood of my sample data or more extreme if the null hypothesis is true. So I saw that there's kind of this 0 plus situation happening over here, that I would experience a sample like this if they were actually as good as that national number of 40%. So this either means that I'm looking at like lottery odds of getting something like this, or they're actually better. Now, same thing going on here. There's still the potential, though, very unlikely, that their rate ends up being 40%. So I could be wrong. I'm probably not, though. All the same, we're making an assumption. It's possible that this claim that I'm assuming to be true is not true. In fact, I rejected it in this case because I thought it probably wasn't true. Unfortunately, we can never be 100% certain in our results here without having an interval that's just kind of really, really boring. This is what I mean by that. I'm going to create a 100% confidence interval here. I think their success rate is somewhere between 0 and 100%. I'm extraordinarily confident in this result. I know that their percentage is going to be something between 0 and 100, but this isn't descriptive in the same way that 59.6 to 73.7% is. So I have to kind of balance my need to be right and my need for precision. And I'm treating those as kind of two different things there. So I just kind of made a chart of everything that could happen for a conclusion here. And I'm going to try to think about which one of these things are considered good and which things are considered bad. So I'm going to look at this block here. And here's what I'm doing with this grid. I'm assuming the null hypothesis is true for this first column. And in this first row, I'm assuming in our conclusion that we rejected the null hypothesis. I'm going to just do little doodles on the side for what's happening. This is what the conclusion is telling me. And this is what is actually true in real life. We usually don't know this column. We usually do not know what is true in real life. I'm kind of assuming something massive when I'm making this table. It'll help me understand the area. So our conclusion, we rejected the null hypothesis. So that tells me that I'm ending up in the second situation for our conclusion, where I tend to believe the alternative hypothesis is true. If the null hypothesis is actually true, I have a bit of an issue, because ideally where I finish my conclusion and what's actually true line up. If they line up, I'm not making an error. But if I'm ending up at different spots where I'm saying the null hypothesis is true for one and the alternative is true for the other, I have an issue. So in this case, I have rejected something that is actually true. I want to retain the truth. I want to throw away lies. So in this case, I would say this is my first error. I'm going to call this error 1. I'm not great at naming things. Let's look at this one here. Suppose the null hypothesis is not true. So I'm going to make another one of these little doodles. If the null hypothesis is not true, then I'm really hoping that I end up at this alternative hypothesis. If I have to believe one of these two things, and I'm being told that this is not true, then I should end up here. So this is the ideal spot to end. Now let's see what happens when I actually do the test. Our conclusion for the test says we reject or we leave this null hypothesis in favor of the alternative. So my conclusion, I was at the HA. For the truth, I was at the HA. I'm ending at the same spot for both. That feels like a great thing to me. This is actually a good situation. I've got 2 more blocks, and I'm going to have you pause the video and try these 2 blocks on your own. If you fail to reject the null hypothesis, and the null hypothesis is actually true, is that a good thing or a bad thing? So this is like retaining the null hypothesis, and the null hypothesis is true. Do you want to retain the truth? This, the null hypothesis is not true, so think of it kind of like null hypothesis is a lie here. And you fail to reject the null hypothesis. Do you want to hold on to a lie? Is that a good thing or not a good thing? So go ahead and pause the video here, give it a minute to see what you can do. I'm going to start going through this problem with you. Suppose the null hypothesis is true, and I fail to reject. I'm holding on to that true thing. That sounds great to me, holding on to the truth. So this is a good thing. This would be one of the 4 scenarios where I do not make an error. Null hypothesis is not true. So this is telling me this top thing here is actually a lie. I'm really hoping I end up at the alternative hypothesis. And let's suppose I fail to reject the null hypothesis. This means I'm holding on to a misbelief here. That's not a great thing. This is actually an error. I'm holding on to a lie in that scenario. This is the second lie to show up in my table, so I'm going to call this a type 2 error. So let's label the different types of errors that I got here. And I'm also going to give them kind of the name in the medical industry. You may have heard of some of those names before. A type 1 error, this is when I reject the null hypothesis, but the null hypothesis is actually true in real life. So in other words, I am throwing away something that is actually true. In the medical industry, this is called a false positive. We're going to do a couple of examples and you'll see why this is called a false positive. But it ultimately has to do with someone being told that they're positive for something when they really are not. Type 2 error. This is when I fail to reject the null hypothesis. So I'm holding on to that null hypothesis, but the null hypothesis is not true. So I'm thinking of this as I'm holding on to a lie in this second situation. And on this first one, it's sort of like letting go of a truth. Both of those things are bad. This is sometimes called a false negative. So if I was testing for strep throat or COVID-19 or anything like this, these would be really, really important terms to understand. The way that I kind of tell these two things apart, because they feel super similar to me, is the number of hypothesis that is true determines the error number. This is really informal. This is just kind of my guide for going through things, but this is what I mean by it. If I'm looking at a type 1 error, this tells me the first thing is true. The null hypothesis is true for a type 1 error. How could that be a bad thing? Well, I make an error by rejecting the first thing. Type 2 error, this tells me that the alternative hypothesis is true, that I should end up here. How could this be a bad thing? If I fail to reject the null hypothesis and end up at the null, when I should have ended up at the alternative, that's a bad thing. Let's look at a scenario involving a pregnancy test. So determine what a type 1 and type 2 error would be for the scenario. Begin by stating the null and alternative hypothesis. And here's the scenario that I'm dealing with. A person tests to see if they are pregnant. So null hypothesis, alternative hypothesis. I'm thinking about real life and sort of what the status quo is. Null hypothesis represents there being no change, or sort of what the norm is. And by default, most people are not pregnant. Under certain circumstances, a person could become pregnant, but it takes an act to do so. If this is something that you don't understand, PCC offers health classes. You might want to think about taking a health class. All right. Type 1 error. I'm going to use my naming trick on the side here. And for a type 1 error, that means the first thing is actually true. So the person is not pregnant. So that's what's going on in real life, but let's think about what the pregnancy test could say. That would be a bad thing to say in this situation. So if the person is pregnant, it would be bad if the test says that they are positive when they are not in fact positive. They would be coming up with a false positive. They think they're pregnant when they're not. Type 2. This would mean the second thing is true of the person. So the person is pregnant. Let's think about how this could be a problem. If the person is pregnant, I would hope that the test determines they're pregnant as well. It would be an issue if the test says that they were negative for pregnancy, because this would mean that they had a false negative for the test. I think both of these situations are bad. In this first situation, someone can start to get ready for a family thinking that they're pregnant, but they're not actually pregnant. There could be a lot of heartache for that. For the second situation, someone could be going around eating sushi, going hang gliding, drinking alcohol, doing whatever here, stuff that you probably shouldn't normally do while you are pregnant because they don't realize they are pregnant. Of these two things, I might be inclined to say that a type 2 error is worse, but this is really, really important. You can disagree with me. Where you are in life, you might actually think, well, I'm trying to get a family ready. A type 1 error would be heartbreaking for me in a way that a type 2 error would not be. So for you, maybe a type 1 error is worse. We'll see where personal opinion kind of will determine what we consider for our alpha later on. We'll cycle back to that. These are abstract when you're starting out, so we're going to do another one or two of these things. I'm going to flip the page and do some more. Determine what a type 1 and type 2 error would be in the following situation. You want to test to see if someone has strep throat. Remember, the null hypothesis is the base thing that would be true under normal circumstances. No change, null hypothesis. The alternative hypothesis is typically what happens if something has changed in the scenario. I'd like you to pause the video and give this a go and see if you can determine what the null and alternative should look like, as well as a type 1 error where the first thing is true and a mistake has been made, and a type 2 error, the second thing is true and a mistake has been made. I'll give you a second to do so. Okay, I'm going to go through this with you. You may see Victor jumping around in the back there. I don't know if I should say sorry or you're welcome. The base hypothesis is that they do not have strep throat. It takes getting infected with this to have strep throat. A type 1 error, this means the first thing is true. They don't have strep. And how could this be an issue? The test says they do. So this is not a great thing. They could start taking antibiotics for having strep throat when they don't actually have strep throat. That's not an ideal situation. Type 2 error. The second thing is true. They have strep throat. And how could this be a problem? Well, the test says they don't. So this would mean the person is actually infected, but they do not think that they are infected. Of these two scenarios, this false positive and this false negative, I think it might be worse to have a type 2 error, for someone to be sick and spreading it without realizing that they're doing that. No one wants to be in that situation. So at least for me personally, I'm more concerned about a type 2 error. You might be more concerned about type 1 error, that as we take things like penicillin, if we have these new strands that are resistant to penicillin over time, if people don't stick up with their regimens for taking their medicine, that could also be an issue. It would be a valid concern to be concerned about a type 1 error there. All right, let's look at another one. Type 1 and type 2 error. Person is on trial for stealing a loaf of bread. the penalty would be $400,000, okay? So kind of the twist on a Les Mis sort of thing. So at least in the US, the way that the court system is designed, the null hypothesis, we assume a person is not guilty until there is evidence to show that they are guilty. So I want you to take a moment and see if you can figure out what a type 1 and type 2 error would look like for this scenario. Pause the video, try it out, see what you can do. Let's take a look. Type 1. The first thing is true about the person. So they are not guilty. So what's a bad thing that could happen to a not guilty person? Well, they are found or told by the court they are guilty. Now let's think about what this means in the context of the fine. So they are not guilty. They did not steal a loaf of bread. And yet they got penalized $400,000 for something they did not do. I would consider this to be a pretty bad situation here. Let's look at type 1. Type 2, second thing is true. If the second thing is true, they are guilty. How could this be a problem? Well, if they're actually guilty, it would be an issue if the court finds them not guilty. So let me think about what that would mean. So they stole a loaf of bread, but they did not get fined $400,000. So if you're really concerned about justice, this would be a bad thing for you. If you're more concerned about justice than incorrectly fining someone, or perhaps your definition of justice includes both those things, you might find a type 2 error to be worse. In these two situations, this is me personally, I think it's worse to charge someone $400,000 for something that they didn't do. So I personally would be trying to avoid the type 1 error more than the type 2. In any of these situations, both errors are not good. It's very rare to have a situation where you kind of luck out and all of a sudden everyone gets candy or something like that. So I have this balance of trying to avoid a type 1 error sometimes and a type 2 error other times. This grace will ultimately come to me when I select my alpha. And here's what's actually going on. Alpha is our willingness to make a type 1 error. So when I say something like alpha equals 0.05, this means I am willing to say that 5% of people that are not guilty should be found to be guilty. It's sort of my willingness to make that type 1 error. So one of the issues though, if I make my alpha something really small here, I don't want to say 5% are guilty when they're not guilty. Even 1% makes me uncomfortable. I might want to do something like 0.001. Context matters a lot here. But if we decrease our alpha level, it is a lot harder to reject the null hypothesis. A couple of things happen as a result of having it be harder to reject the null hypothesis. If I'm less likely to reject, I'm more likely to say they're not guilty. If I'm more likely to have them be found not guilty, then this means that type 1 error is less likely. Because I want to be really, really sure before I have any sort of a conclusion to that court case. On the flip side, though, this means I'm way more likely to make a type 2 error. So if I start saying that everyone is not guilty, there might be people that are stealing bread that are starting to get away with stealing bread. In the case of this, if I use a really small alpha level and I'm telling everyone that they don't have strep, there are going to be a lot of people out there in the world that have strep and they don't realize it. So in the situation where I think a type 1 error is worse, I do want to decrease my alpha. I want to use a small alpha level. This will make it less likely to make a type 1 error, but it's going to make it more likely to make a type 2 error. Type 1 and type 2 just kind of go in opposite directions on me. If we think a type 2 error is worse, we should use a large alpha level. If I use a large alpha level, this makes it less likely to make a type 2 error and more likely to make a type 1 error. And we're going to see that there's a bit of a balancing act that goes along with this. So if I'm talking about a small alpha level, 1% or smaller is usually considered to be pretty small. This is kind of on par with being 99% confident. Large alpha, say 10%, this is kind of on par with being 90% confident. If I make my alpha too big, my confidence just kind of tanks on me. If I make it too large, my interval gets so big that it's no longer useful. So I had the same balancing act that I had for my confidence interval happening here with my alpha level. If both things seem equally bad to you, type 1 and type 2 error are both bad for you, then I would use an alpha level of 5%, being kind of 95% confident, as our base definition for what it meant for something to be usual, a neutral alpha level. I've already identified for this court system that I might only want to say this for 1% of people. Let's go back and consider example 3 for a second. In example 3, we said a type 2 error was worse. If I think a type 2 error is worse, I should be using a large alpha level. So if I was doing this hypothesis test, I want to be more inclined to reject that null hypothesis in favor of getting people treatment. So I am more likely to say that people have strep here than if I had an alpha level of, say, 1%. Again, that's my balancing act. If you look down the whole page, there's almost no math calculation part that's going on with this. But the whole thing is really math. This is the nuance of statistics. As I'm going through all of this vocab and I'm practicing the language. We have a run by Victor. Hey, thanks, bud. Okay, we're going to flip the page and look at page 4 here. A tiny bit more vocab. This is the end of the vocab for this stuff today, so don't panic. We're in the home stretch here. Alpha is the probability, or at least my threshold or willingness of making a type 1 error. Beta is my probability of making a type 2 error. So you can think alpha is linked with my likelihood or willingness to make a type 1 error. Beta is my probability of making a type 2. A for 1, B for 2. The probability of not making a type 2 error, and I'm hoping that I don't make any errors. I'm hoping I don't make a type 1, I'm hoping I don't make a type 2, but this actually has a special name. The probability of not making a type 2 error is called the power of a test. And sometimes for stuff like pregnancy tests or strep throat tests, you can actually look up what the power is for that, and it tells you the likelihood that you're avoiding that situation that you really, really want to avoid. You're avoiding that false negative. Since the power is sort of the opposite of beta, I have 1 minus my beta. This is probably something that you're going to have to go through 2 or 3 times. Otherwise, you might get a little bit of kind of alphabet soup when it comes to this. But let's just see kind of what happens as I increase my alpha with all of this type 1, type 2 beta power situation. So if I increase my alpha, then it is more likely that I make a type 1 error, and it is less likely that I make a type 2 error. If I am less likely to make a type 2 error, then my beta goes down. My alpha and my beta go in opposite directions. If I'm less likely to make a type 2 error, then my probability of not making that error has gone up considerably. So my power increases. Make your alpha bigger, you make your power bigger. What happens if alpha gets smaller? I'm going to ask that you pause the video, take a minute, and go through these same logical conclusions here. What should happen to your type 1 error? What should happen to your type 2? What about your beta? What about your power? Let's try it together. If alpha is less likely, and alpha is my threshold for a type 1 error, then I am less likely to make a type 1 error. If I'm less likely to make a type 1 error, then I am more likely to make a type 2 error. If I'm more likely to make a type 2 error, then I have less power. My power has decreased. And the reason why my power would decrease is my probability of that type 2 error has gone up. Now, if you're looking at this and you're thinking, well, this is kind of hopeless when it comes to this alpha. No matter what I do, I just seem to be increasing the error. There's actually one way that I can decrease both the likelihood of a type 1 and a type 2 error at the same time. And this might not come as a surprise to you, but I could increase the sample size. So if I want to be more sure of my results overall, regardless of if I'm doing a hypothesis test or a confidence interval, the more people I ask, the more evidence I have, the more likely I am to make the right conclusion. Flip a coin once, hard to tell if that thing's fair or not fair. You flipped it 1 billion times, you probably have a lot of evidence going on at that point. I promised you I'd show you the connection between alpha and C. Let's look at that connection together here. So I'm going to start out with pretending that I'm doing a two-tailed test. Reminder, a two-tailed test is going to happen when you have an alternative hypothesis of not equaling a value. I find that it helps to draw pictures for these, so I'm going to do that. Alpha is the size of your tails for the test. Your confidence happens in the center. So if someone says, I want to be 95% confident, then they're saying they want 95% in the center. This is a two-tailed test, so I'm shading in my two tails. If I have 95% in the center, that leaves me with 5% for both of my tails. Let's do another one with a confidence level of 90%. I start with 90% in the center. These pictures are not to scale. I just drew 90% bigger than 95. I'm going to shade in my tails. I'm actually going to fix that as I shade in my tails. thinking on the fly. If I have 90% in the center, the entire curve is 100%. That leaves me with 10% for my two tails in total. Just as a note, if I was doing a one-tailed test, that would be 5% in one tail. If I'm doing a two-tailed test, that's 10% in total. Here's what this means so far. Let's say I do a hypothesis test and I want to use a neutral alpha level of 5%. Well, then when it came time to follow that thing up with a confidence interval, I don't have a choice. I should follow that up with a 95% confidence interval. Otherwise, my results might not match up. If I just did a test with a large alpha level, say an alpha of 10%, this would force my hand when it came to confidence level for my confidence interval. I would want to make sure that I'm 90% confident. The third most common confidence level is 99%. I think you might see where this is going. Little tails here. 99% confident in the center. If I have 99% there, I'm way out in the boons and I have 1% remaining. So if I use a really small alpha level of 1%, then I have to be really, really confident to reject the null hypothesis. If I have a small alpha level, I do not have to be as confident to reject that null hypothesis. The opposite of alpha, or the complement of alpha, is C. So 1 minus C is my alpha, 1 minus my alpha is the C. This is true if I'm dealing with a two-tailed test. Let's consider now a one-tailed test. So in a one-tailed test, my alternative hypothesis is either going to be less than a number. This will cause me to have just the left tail shaded in. Or I have greater than a number. This will cause my right tail to get shaded in. Now, when I'm drawing these pictures, I'm still going to start with C in the center. So suppose I want to be 95% confident. That means I have 95% living in the center. My alpha is going to be the size of one of the two tails. So my two tails together are 5%. But if I'm only looking at a single tail, that's 2.5%. Let's look at another example of this. Suppose I want to be 90% confident. That means I want 90% in the middle of my curve. Again, let's suppose I'm looking at a one-tailed test. I'm just alternating, thinking sometimes it's going to be less, sometimes it's going to be more. But if I have 90% living here, that means I have 10% left over for these two tails. So just a single alpha would be 5%. If you're looking at this and you're comparing it to the results before, you'll see that all of my alphas have been cut in half. 5% went to 2.5, 10% went to 5%, and finally, if I wanted to be 99% sure, this leaves me with an alpha level of 1%, because I have 1% left over for these two tails, split in half, which would be 0.005. So my alpha level and my confidence level, they're linked forever. I'm going to just try one more of these things, but I'm going to go in the opposite direction. Let's suppose I start with an alpha of 1%. This would be a small alpha level. This would be something that I might want to use if I was really concerned about type 1 error. And let's suppose that I had an alternative hypothesis of less than some number. If I'm drawing this picture, this is a one-tailed test, and it says the size of this one tail is 1%. If I wanted to know what confidence level I should use, Well, reminder, confidence is always in the center, so I'm really trying to find this spot here. If I have 1% here, even though this isn't shaded in, this other spot that I wouldn't want here is 1%. 1 and 1 gives me 2. 2 leaves me with the remainder of 98% in the center. So when I want to come up with the confidence level for a one-tailed test, I'm going to take away that alpha level for both sides, because it's only giving me half of the area as normal. So I have to double it to get that total area to remove. If I'm dealing with the confidence first, if I do 1 minus the center, that gives me the size of 2 tails. To make it a one-tailed test, I would have to split that in half. Even though I'm giving you these formulas here, I really think it helps to draw the picture more than actually memorizing these things below. Let's look at a final example, and I'm not going to do this whole thing. I'm just going to really concern myself with setting up the null and alternative hypothesis. I want to know what a type 1 and a type 2 error look like. I want to select my alpha, and based off of my selection for alpha, I want to figure out what I have to have for sure as my confidence level C. So due to the unexpected weight of keychains, several Chevy brand cars had to get recalled. This actually happened to me. So what happened is the weight of the keys would actually jangle out the key from a running car. So my car would still be running, but I would not have a key in it. Luckily, this didn't happen to me, but it happened to a lot of people throughout the nation. So let's suppose that it was determined that about 20% of all Chevy cars had this problem. And they hope that they have made things better. So they've hoped that it happens now for less than 20% of cars. PR specialist tests 200 cars and finds that 25 of them still have this problem. They want to test if the company has improved, and before going public, they want to make sure that they've had a lot of evidence that they are on the way to improvement there. So let's think about in words what a type 1 and type 2 error would mean. Type 1 error, that means the first thing is true. If the first thing is true, this means they have not improved. They still have a 20% or worse success rate. So what could be wrong if they've not improved? Well, they could think they have. So they're telling people, hey, things have improved, when really safety has not improved. That feels like a pretty bad thing. Type 2, the second thing is true. They have improved. So the safety of their cars has gone up. That seems like a good thing to start out with, so how could this be bad? Well, they could think they have not improved. So they keep working, they keep spending hours and labor to try to make things better, even though they've already achieved their goal. They've already made things better. So what could be the problem here? Well, we want to test and we want to make sure that there's a lot of evidence before going public. So they don't want to say things have gotten better when they have not gotten better. So this sounds like type 1 is worse. And sometimes we have those days when we misspell words like worse. That happens. If I think a type 1 error is worse, I'm going to use a small alpha level. I want to try to avoid that. So an example of a small alpha level might be something like 1% or 0.01. Let's try to figure out what our confidence level should be to match up with this. Well, I'm drawing my picture. My alpha level, and this is going to be pointed to the left, so left tilt test. I'm willing to have at the absolute biggest a tail of 1% here. I want to be really, really confident before I say that things have improved. So it's not going to be surprising if I have a large C level here. I want to be confident. C lives in the center. If I have 1% here, I also have 1% in this tail that I don't want to include because I only want the center chunk. 1 and 1 makes 2. That leaves me with 98% as my confidence level. I have my alpha and my C, so what's left to do? Well, I'm going to ask that you, on your own, try to perform that hypothesis test and check with that alpha of 1%. Do you end up with a p-value that's larger or smaller? I also want you to follow it up with a confidence interval. Do you end up getting 20% inside of your interval, or is your interval less than 20%? That's equivalent to doing the hypothesis test, and you should get the same results both ways. I've now looked at both test and coming up with intervals and what could go wrong with those intervals. Next time, I'm going to start to consider two proportions at the same time. I want to know, is my success rate for the first group higher or lower than my success rate for a second group? So more on that in the next video.